Okay, so let's think of the concept of the average value of a quantity in quantum physics. So let's sort of argue, to begin with, by analogy with, say, the average value of 10 exams. So let's say that you take 10 exams and on half of these exams you get 80. So the average would be that 5/10 gets multiplied by 80. Let's say that 3 out of 10 you get a 50. So 3/10 times 50, and the remaining 2 you get 100. So on 2 out of 10 you get 100. And so this is a weighted average of your different scores, and that of course gives us 75 as your average. Now in quantum physics things are a little bit different, because if I make a measurement on some quantum system and get some value for say the position of an object, and then I make the measurement again, I'll keep getting the same value. So the notion of an average needs to be sort of generalized, and it works something like this. You want to have sort of the equivalent of this kind of calculation would involve 10 different quantum mechanical systems that are all in the same state initially, and then you perform a measurement on all 10 of them and see what you get. And so the average, we'll call this average a little bit different in the sense that it involves a whole bunch of different systems that were initially in the same state, and so we call it the expectation value. But by analogy with this is sort of the intensity of this grade, right? The intensity of this grade is this, and the intensity of getting 100 is this. And so we multiply the value of the position times the intensity for that position, which is just psi of x and t modulo squared, and we integrate that. Okay, so that is what we call the expectation value, or average, in quantum physics for the position. So let's think about this quantity. How does the expectation value vary in time? So I'm going to take the derivative in time of this quantity. So I'll get minus infinity to plus infinity times x d by dt of psi of x and t, that's where the time dependence is, modulo squared in dx. And this looks like, let's just write this out so we can apply the time operator, the derivative operator, on the two terms that make up psi of x and t modulo squared. So I'm going to be taking the time derivative of psi star psi and integrating that. But this is minus infinity to plus infinity of x times psi star, right, times, we apply the chain rule, so I apply this to the first term, psi, and then I apply it to the second to get d psi star dt times psi, and integrate that. Now we look at these time derivatives, and we want to integrate in x. So we want the x dependence of all of these terms, And so we can use the Schrodinger equation, which says that I h bar d psi dt is equal to minus h bar squared over 2m, two derivatives in psi with respect to x plus v times psi. And so from this, we can say that d psi by dt will be I h bar over 2m, two derivatives minus I over h bar times v times psi. And for the other time derivative, d psi star by dt, then this would be minus I h bar over 2m, two derivatives in x of psi star, plus I over h bar v times psi star. And so, let's see, we're constructing psi star times d psi by dt, and that is, in terms of x dependence, it's I h bar over 2m psi star d2 psi with respect to x minus I over h bar, the potential, psi star psi, and d psi star with respect to t psi is equal to minus I h bar over 2m, two derivatives in psi star with respect to x, plus I over h bar v psi star psi. And so now we can write the term that we're looking for that's in the parentheses here as we have psi star d psi by dt plus d psi star by dt times psi is equal to I h bar over 2m times psi star d2 psi in x minus d2 psi star in x psi. And so let's plug that in and get that the time derivative of the expectation value of x to be I h bar over 2m integral over the entire space of x times psi star times these two derivatives in x of psi minus this in the x. And we can think of this as the derivative in x of some quantity so that we can then integrate by parts. So this is I h bar over 2m, the integral over the entire space of x times, if you want to think of this as the derivative in x of something, then it will be this times the first derivative in x of this minus the first derivative of psi star with respect to x times psi. that's the term that goes here. So it's right. You want to make sure that you can see this by applying that spatial derivative to this object. And let's just think about that for a second. When we apply it to the second term, we get the second derivative here, like that. And we apply it here, we get the second derivative of this. It looks just like that. But we have to also apply it to this. Right, so we get deep psi star with respect to x times this, minus this times deep psi with respect to x, but that cancels because they're the same thing. So we can write this thing in parentheses as the time is this d by dx of this term, and then we can do by parts. We can get psi star deep psi by dx minus deep psi star by dx psi, which we have to integrate at the extremes, minus to plus infinity. Evaluate at the extremes. It looks like that. Minus, we'll see, what do we have left? We have this part. So we have to integrate the part that's in the parentheses. Minus to plus infinity of psi star deep psi by dx minus deep psi star by dx psi. But this term has to vanish because we know the wave function has to bend to represent a localized particle. It has to bend to 0 before we get to plus or minus infinity. So it has to be the case that psi and psi star are equal to 0 at x equals plus or minus infinity. Either one, both of them, it has to be true. Otherwise, the particle is non-localizable. So this, all of this disappears, and all we have is this. But we can also notice that minus infinity to infinity of this part in dx, right, we look at this by parts, then it becomes psi star psi evaluated at plus and minus infinity, and that has to vanish for the same reason. That the wave function needs to represent a localized particle, so it vanishes at infinity, minus the integral of psi star deep psi by dx. And so the integral of this part looks like this part, and so we actually get a factor of 2 here. And therefore we can say that the expectation value of x in dt is equal to not minus I h bar over 2m, but minus I h bar over m times the integral from minus to plus infinity of psi star deep psi by dx, right, twice that term in dx. And so notice that if I just multiply both sides by m, I'll get m, the expectation value of x in t, but that's, so m dx dt, right, that's the expectation value of the momentum p, and so that is minus I h bar minus the plus infinity over the entire space of psi star deep psi by dx in dx. And so let's take a moment to understand this function, or both of these expectation values. So the expectation value of x and the expectation value of p, right? The expectation value of x can be written, it was x times psi of x modulo squared in the x, so I can just write that as psi star x psi in the x by sort of sandwiching the quantity whose expectation value we're trying to find, and that sort of lends itself to comparison with the expectation value of p, which also appears like it's being sandwiched. It's like an operator that's being sandwiched in between the psi star and the psi. So you can sort of think of the position as the position operator and this other quantity as the momentum operator.